So we are starting our class today about CMOS amplifiers, and let's start with revising the CMOS architecture, where how it's being structured and formed on CMOS metal semiconductor. So basically, you remember from last semester that we have two N wells and on a P substrate. This is for the NMOS, and vice versa. It will be for the PMOS, where we have the P wells and the N substrate. So these devices, basically, they are symmetric. So you can change the name of source and drain arbitrarily. Just they will become a source or a drain really once we bias them with a certain voltages. So normally the drain have higher voltage compared to the source. Now, what we care mostly about these devices, how they are operating, what operating region they are in, because they will decide what behavior they will have, like how they will act in our circuit. So basically, these behaviors or these operating regions, they will be changed or they will be decided by the certain voltages that we are applying on these devices. So once we have this is the gate, and this is the drain, and this is the source. So how we are setting our VGS and our VDS, those they will decide how or what operating region our transistor is. So if VGS first has to be greater than V threshold in order for the transistor to turn on. Now, when VGS minus this V threshold, this difference, we normally call it the V over drive voltage. If this is greater than VDS, then we are basically on the linear region, or sometimes we call it triode region. Now, if this is less than VDS or VDS greater than this overdrive voltage, then we are operating in the saturation region. Now, each of these operating region is useful for a certain functionality that we are going shortly to talk about. But now, so in this graph, you can see that when VDS, this is our VDS, this is the VDS, it's smaller than VGS minus this V threshold. So we are here when VDS smaller than VGS. This is our triode region. And when VDS is greater than this V overdrive, then we are in the saturation region. And the current of the transistor, it's following from here, this is ID, is basically going to be decided according to this operating region. So in case of the saturation region, ID will be equal to half mu n COX W over L VGS minus V threshold. Now this is mu n, if you remember, it's related to the mobility of the electrons, and COX is the capacitance of the oxide capacitance, the gate capacitance, and W over L is the width over the length of the transistor, and VGS minus V threshold is the overdrive voltage of this transistor. And you can see it's a quadratic relation. Now in the linear region, here in the triode region, basically you can see that there is a linear relationship between the VGS minus V threshold with the current. So it's not raised to power 2. Now this is VDS is squared, but we are mainly talking about the VGS in relation with respect to the VGS. Now, when the transistor is operating in the linear region, it's basically act as a switch. So linear, it's normally, we use it as a switch application, and it has a certain linear resistance for it that's given with this relation. So it's 1 over, I think mu is missing here, mu and COX W over L with a VGS minus V threshold. There is some typo in this relation, I'll fix it. So normally at small VDS, the transistor can be viewed as a resistor with the resistance depending on this gate voltage, the VGS. Now again, we use it as electronic switch in multiple applications. For example, we use it in the switch capacitor circuits. That's a type of circuits that we have a lot of applications. It can be also used in the RF applications, where basically if you want to connect, this is an antenna. So instead of having 2 antennas, you can have a single antenna, and one time you can connect it to a receiver, and one time you can connect it to transmitter with the means of a switch. So having a transistor here that is basically operating in the linear region is basically can act as a switch. So one time we can make it open if the VGS is below the V threshold. This means it's going to be open. And when VGS is greater than V threshold, VGS greater than V threshold, it will be basically the switch is closed and it's functioning as we want. So the connection is there, but we have to make sure that VGS minus V threshold is greater than VDS. So it's not in the saturation region. Now, obviously, when it's act as a switch, we need to make sure that the switch has very, very small on resistance. So it does not take or load our antenna. You can think of it as a voltage divider. So we want all the voltage to come here from Vn into V out. So V out equals to R antenna divided by R on plus R antenna. So in order multiplied by Vn. In order for most of the voltage of the Vn to be arrived at the V out, we want this is R on to be as small as possible. If it is 0, which is a very, very ideal case, it's not. This is almost very near to 0, let's say. Then R antenna over Rn will approach to 1, and therefore V out will equal to Vn. But again, this is an idea, it's not the case. Normally, there is even a little impedance, but it's there. And in order to reduce this impedance, as you remember from the relation that we discussed here, either I make VGS minus V threshold is large, or I increase the W value. So normally we have a larger width transistor in order to act as a switch with a small on resistance. Okay, so normally we need to test the amplifier to make sure again that VDS should be greater than, VDS should be greater than VGS minus V threshold in order to operate in the saturation region. And when VDS is smaller than VGS minus V threshold, then we are in the triode or linear region. So we need to do this check in order to decide what is the operating region of our transistor. Now we have seen that, yes, this is the same thing. And we have seen that it's useful for us to, the transistor, when it's operating in a triode region, to act as a switch. But what is the advantage of operating in the saturation region? This is when our transistor basically acts as an amplifier, and we will discuss that soon. Now, sometimes we have assumed that our current in the saturation region is given by this relation. However, sometimes, especially when the short channels, when L is short, or we have an effect that's called channel length modulation. So basically the length of the channel becomes shorter, and this basically reduces the impedance of the channel, and therefore the current increase. So we are not, the current is not given by this relation, it's going to be given by, again, I don't know why these are missing. So there's no square here. Yes, so basically the current will be given by this relation. So there is lambda here, this factor that's going to be added on the current calculation. So the current will be increased, not only this relation, but multiplied with this factor that is here. I'll fix these issues on the slides. Okay, so there is one also important aspect of the current, the amplifier or the transistor, which is called transconductance, and normally we give it the symbol small gm. So the transconductance is a measure of how strong the drain current changing with respect to changes in the gate voltage, and normally it's given by multiple relations. Again, same issues. Why mu1 is missing everywhere? Okay, again, don't know why this is happening. Okay, so these are the relations that's given for the basically the GM, and where are they come from? They basically came from this relation here, that the GM is the derivative of ID with respect to VGS. So now when we have the relation that, ID equals half mu1 COX W over L VGS minus V threshold square. So now when we're going to derive this ID, dID over d VGS, so everything else will be considered as a constant except VGS is the variable. So it will be half mu1 COX W over L. Now that square will come out 2, and this VGS minus V threshold. So now the 2 will go with the 2, and this is equal to GM, and this is the relation that basically given here. Now you can also, if you do some adjustment, like if we replace this term, the VGS minus V threshold here from this equation by taking the square root of the two sides, then we can replace it and we can reach to the relation that is given here. Similarly, you again replace the VGS with the V threshold, and we can reach to the third. So they are interchangeably, I mean, they are all correct. So now we want basically to study the behavior of this transistor as an amplifier. And since they are nonlinear circuit elements, we need somehow to look at the linear or a portion of its operation that we can, in this small range, consider it as a linear, if this is possible. And in order to do that, there are two models that they help us. The first is called large signal model, and then we have the small signal model. The large signal model is basically useful to decide the operating region. Means in the large signal analysis, we decide what is the operating region of this transistor. Okay, so is it in saturation region? Is it in the triode region, or in the cutoff region? I mean, the transistor is off. Now, when it is in the saturation region, it is here in this condition, this is saturation. And basically we have VGS greater than V threshold, the transistor is on. We have VDS greater than the overdrive voltage, VGS minus V threshold, and the current will be given by this relation. So it's half mu and COX W over L, VGS minus V threshold square, multiplied with the channel length modulation effect, if we are assuming that we want to take care of it. If we assume lambda equals 0, then this term will be goes to 0 here, and this is 1 plus 0 is 1, and therefore it's not affecting us. Now, when the transistor is basically here in the triode region, so we have VGS greater than V threshold, transistor is on, but VDS is less than VGS minus V threshold, and the current is giving in this linear relation with respect to VGS. Now we have this region, they call it deep triode. I mean, the naming is not so super important. In triode or deep triode, both of them are triode. But here, basically, the difference is that VDS is much less than 2 times VGS minus V threshold, and the transistor is basically act in as a switch again, and it's have this resistor, linear resistor. Now, why this much difference? Because we said in order to have a small on resistance of the switch, which is desirable, we need to increase the VGS minus V threshold, this part, so that the transistor resistance is very small. Okay, now the other is the small signal model. Now, after we know what is the operating region of our amplifier, and we assume that it is in the saturation region, now here, in order to be as an amplifier, we can study how much gain it will give us, what is the input and the output impedance of this amplifier. So, and obviously the transistor should be operating in the saturation region in order to behave as an amplifier. And for that, we look into the small signal model. Here, assuming that lambda equals to 0, and here lambda not equal to 0. So we assume that the transistor is behaving as a current controlled voltage source, and it depends, the current will be changing with respect to VGS and the transconductance of the amplifier, which is, or the transistor, which is GM. And it's going to have a parallel resistance that's called R out. And this R out is basically equal 1 over lambda ID. So if lambda is equal to 0, then this R out will be infinity, and that's why we are not including it here in this model. So we can assume that it's having basically an infinite resistance. And again, this is basically assuming that our transistor, we have decided that's working on the saturation region, and the input signal is very small, that it's not going to change this operating region. Let me clarify this more. Okay, I need to clarify this. Now it's from another book reference. Okay, this slide has been destroyed here. Okay, that's bad, but not so bad. Don't focus too much on this, what's going on here at this moment. It's not important. What I want you to look on this graph here is basically in the large signal analysis, this VGS is free to move here and there as much as it wants to move. So wherever this VGS is lying, we are going to find, find also the VDS there. And we look for a VGS, for a value of the VGS that is going to achieve that VGS is greater than V threshold, and VGS minus V threshold should be less than VDS. We need to identify those two conditions so that our amplifier is in the, or our transistor is operating in the saturation region. So we found that this is a good point here, and this is our Q point or quisecant point, or the DC bias, DC operating point, or the bias point. It has all these names. So this is the value of the VGS that is going to be greater than V threshold, and VGS minus V threshold is less than VDS. So these conditions, they are decided in the, as I mentioned, in the large signal analysis. Large signal means that we are talking about large voltages that they are deciding these operating conditions. Now, okay. Now, once we decide this large value of the VGS, we can basically operate around it in this small region, where basically our behavior is as a linear line here. As you can see, this red line, we are, if my input signal is basically small AC signal around this DC value, I only have this small amplitude around changing, can change my signal around these values, then my transistor will behave as an amplifier. Okay, I know that this sounds not so clear. Let's try to explain it here. Oops, yes. If you look at this circuit, so I have an NMOS here. This is the gate, and this is the source, and this is the drain. Okay, so I have a DC voltage that is basically a large voltage. Let me give values. So here, this is 0.7 volt, and the threshold of the amplifier is 0.5 volt, okay? And I assume my amplifier, my VDD is, let's say, 1.8 volt, okay? So now my VGS is, the source is connected to the ground, so my VGS is equal to 0.7 volt. Why? Because this this S is grounded. Now somebody's saying, what about this small VGS? Now I will discuss, assume at this moment that it's not here. We'll discuss it in a while. Now, let's assume that ID multiplied with the RD is, let's see, 0.6 volt, just the voltage drop across here. So let's do the check. 1.8 volt minus 0.6 volt is equal to my VDS. Just a simple KVL, you can reach to it. And this is equal to 1.2 volt. And this is greater than VGS minus V threshold, which is basically 0.2 volt. 0.7 minus 0.5 is equal to 0. So this amplifier is operating in the saturation region. Now, so it is acting as an amplifier and all that good. Now, this is the value of the VGS, and this is the value of the VDS that they are ensuring that we are in the operating region. Now, but we said that we want this device to act as an amplifier. So what do I want to amplify? Do I want to amplify the 0.7 volt? No. So the 0.7 volt is not the voltage that we want to amplify. There is a small AC signal that has an amplitude of very small amplitude, let's say 1 millivolt amplitude or 0.1 millivolt. Yes, I mean very small signal that can be, we have an AC, it's an AC signal that's varying basically, and we call it, it's riding on top of this AC signal. So this DC, so our input will look like this. Sorry, not like this. This is a DC value. So here the 0.7 volt, and it's changing around it with 0.7. This is 700 millivolt. So let's assume it's 1 millivolt, 701 and 0.699. So it's changing between these, the voltage that is reaching to the gate here. And therefore, we usually amplify this small signal, small AC signal with 1 amplitude. So if my amplifier is basically having a gain of 10, so at the output, we will have a small an amplified signal, which is 10 millivolt amplitude. So 10 multiplied with the 1 millivolt, it will be amplified. That's why this is the small signal. And this is the large signal. So in the small signal, we deal with the small signal behavior in terms of the gain. That is, we're going to amplify it. And in the large signal, we deal with these large voltages that they are going to bias the amplifier and change its operating region. And I mean, changing in 1 millivolt will not going to change this operating region of the amplifier. But if I change this 0.7 volt, it will change the operating region of the amplifier. For example, it has reduced by 0.2 millivolt. The amplifier is not going to be on, or it's not going to be in the saturation region. So I hope this is clear. We can stop here for a while to have questions if you have. So that's why here we have the signal is only varying slightly around this VGS value, as we mentioned here, from 0.699 to 0.71. They are moving around it. If this is not clear, we can try to clarify it more. And you can see here the output signal is being basically amplified of this small varying signal. Okay. And the gain basically is going to depend on the slope of this linear region. So if it is gain is high, we have a higher slope, we can only cater smaller range of this small signal. While if the gain is low, I can cater a wider range of my signal. If we just take an example, if my input signal is, let's say, 1 millivolt, and I have, so if I have 1 millivolt and my gain is basically 100, so I will have an output that is 100 millivolt. But if my signal changing is, let's say, 10 millivolt, I will have 1 volt signal that is varying. So I will be limited by the supply voltage. We cannot have a gain amplification that is beyond the supply voltage of the amplifier. Otherwise, we will saturate the amplifier, as we call it. Okay, now if you have any question, we can also take it here. Before we move to the amplifiers, I think you have also covered these, but we will revise them because it's important for us to know these amplifiers in details. We will deal a lot with them, and this is the more, like we are starting here, the most important and the things that you really need to know in order to be able to understand the course further. So what I usually advise a student is that, especially the initial lectures, you need to revise them very soon before the next lecture. Otherwise, when we will become fast, it will be very difficult for you to follow up what's going on. So we don't want anybody to be lost in the class. So a good tip for you here is that you really need to revise these before the next class comes. Okay, so the first thing, when you look at any amplifier circuit, since we have multiple types of amplifiers, you need to identify which amplifier is this. And then you will know in your mind, we will derive the gains and the input and the output impedance for each type of amplifier. You will quickly know what is the gain of this amplifier. We don't need every time to derive these relations, but we are going to do them for the first or second time, but we are not going to do it every single time. Therefore, it's important that you store them in your mind and know the gain of it. The first and the most simplest one is the common source amplifier. How to identify a common source amplifier? You will know that the input is coming on the gate and the output is taken from the drain. And here the simplest case is when the source is grounded. Now, in order to identify the gain, usually we give it the simple AV. AV is basically the V out divided by Vn. And the way that we can derive this gain is from drawing the small signal model. Again, since we are here doing the gain, we will deal with the small signal model. We already knew that this amplifier is going to be saturated by setting correct values of VGS and VDS. Now, how to derive this? We can use the Kirchhoff voltage laws, KVL and the KCL as required, and we can identify from the small signal model what is the ratio of V out over Vn. Okay, so here basically V out, you can see the same current that is going in RD is the same as GM V1. So the current, the V out will equal minus GM V1 times RD. Now, why this minus sign? Because the current direction is in this way. If it was going down, then it will be a positive sign. So now, how V1, I don't need the relation of V out over V1. We're interested with the V out over Vn. So how V1 is related to Vn, you can see that if we make in this loop KVL, we will be having minus V1 plus Vn equals to 0. And this gives me that Vn equals to V1. So I can just simply replace it here, and we will get V out equal minus GM Vn times RD. So V out over Vn, which is the gain, equals minus GM RD. So this is a very important relation. You need to know with that the gain of the amplifier of the common source amplifier is equal minus GM RD. So it depends on the transconductance of the transistor, and it depends on the load impedance, which is here RD. Now here we were assuming that, as you can see, that there is no R out. We assumed, since there is no R out, we assume that lambda equals to 0. Okay, so since lambda equals to 0, the gain is equal minus GMRD, and AV is equals, if we replace the relation of the GM with that relation that we discussed it earlier, we will reach to the same. I'm again apologizing for this mess up that's here, but I'll upload a clean slides. Okay. What was this? Yes, here we need to make sure that the amplifier is basically operating in the saturation region. And in order to do that, we need to make sure that the voltage drop across RD is basically going to be VGS. So it was supposed to be like this. So this is the VGS. So this is VD. And Vs is equal to 0. So this Vd is equal to VDD minus RD times ID. Okay, and Vs is equal to 0. So VGS is minus V threshold should be less than VD S. And since Vs is equal to 0, this is also equal to Vd. So we will have VGS minus V threshold should be less than VDD minus ID times RD. And therefore, if I move this to the other side and this to this side, we will have that RD times ID should be always less than VDD minus VGS minus V threshold. So this is a less than. Okay, in order to make sure that the transistor remains in the saturation region. And this problem is basically, we call it a voltage headroom problem. So in order to have more wider range for this RD, ID, we need to have a larger supply voltage. And usually we are limited by the choice of the supply voltage because it will also decide our power consumption. So in order to have a larger gain, again, we said from the previous relation that was here, we need to have a larger RD value. But larger RD value, we cannot go very much large because we are limited with the supply voltage that we have. Otherwise, we may leave the saturation region. So you can see here that we have a trade-off. So we, for one side, we want lower RD so we can be more relaxed in terms of saturation region. But for the gain, from a gain point of view, we want to have a larger RD in order to increase our gain. And this problem, we usually again call it voltage headroom problem. And okay, so these are the things that we're talking about. Now, what about finding the output impedance of this amplifier? For finding the output impedance, we usually short the input, and from the output side, you apply a test source equal named Vx that have a current Ix, and the R out will equal to Vx over Ix. Again, let me clarify it here. So for finding the output impedance, R out, you need to short the input, step number 1. Step number 2, you need to apply a test source from the output side that is named Vx and have a current Ix, and your R out will be Vx over Ix. So now we can try to do that in order to basically find the output impedance. So Vx is also equal the voltage drop across here. Now, since now the first step is to discuss what is V1 here. V1 is basically both sides of V1 are grounded. So V1 is equal to 0 since we have shorted the input, and therefore this current source is basically 0. So no current is coming here in this branch, and therefore the entire Ix is going through RL, and therefore Vx is equal to Ix multiplied with the RL, and therefore Vx over Ix equals to RL, and this is the output impedance of this amplifier when again lambda is equal to 0. Okay? So here the output impedance is same as the load impedance, the same as RD, which is appearing here. Okay, I think now we're supposed to do it. If lambda is not equal to 0, this means we have the addition of R out here. And the thing now, again, V1 is equal. So we shorted the input, we applied the test source, and V1 remains equal to Vn, which is 0 here, and therefore no current going here. So we have this short side is grounded, and we have Vx equals to RL in parallel with the R out, because two resistors from this node to ground. One side, this is a common node, and the other side is grounded. So they are in parallel, and they are multiplied with the Ix. So R out equals Vx over Ix, and it equal to RL in parallel with the R out. So now from this side, this is the RL, this is the VDD, and this is grounded, G, V out. Yeah, just by the way, you can see now that VDD in the small signal model, since it's a large value that is a DC value that is not changing, we replaced with the ground. Remember that part, it's important. And now V out is basically, if we are looking from this side, we see up, this in the small signal model, it's grounded, and down there is an R out. So if we are looking from this side in the middle, we see up RL to ground and down R out to ground. And looking from the middle, we see their parallel combination. I'll slowly show you how we do this very quickly without the need to do the derivation. So the input impedance, we have not yet discussed the input impedance, but it's infinity. We'll discuss it later. Okay, so I think we can stop here, and next time we can continue discussion.